302, the cylinder of doom. In this laboratory, 24 pressure sensors were used to characterize the flow over a cylinder placed inside the California Polytechnic State University low-speed wind tunnel. In this video, we are going to begin by explaining the setup of the experiment, how we collected the data for this experiment, the data analysis, and error analysis. The goal of this experiment was to collect information on the coefficient of pressure, the coefficient of drag, Strouhal number, Reynolds number, and how all these relate to the examination of the vortex shedding that occurs around a cylinder. Setup. Inside the wind tunnel, there is a cylinder which is loaded with 24 pressure sensors. Each pressure sensor is separated by an angle of 15 degrees laterally. This allowed for pressure measurements around the entire circumference of the cylinder. By utilizing a smoke rig and laser sheet device, smoke was sucked into the test section and over the cylinder while being illuminated by the laser sheet on top of the test section for flow visualization. After running and collecting data for each velocity, a sandpaper strip was then placed on an optimal angle on the frontal area of the cylinder in order to trip the flow and re-energize the boundary layer to keep the flow attached around the cylinder longer. How we collect the data. The tunnel was run at 4 different RPMs, creating 4 different Reynolds numbers over the cylinder. The scanner valve connected to all the ports on the cylinder, logging the pressures on the laboratory computer. Unfortunately for our group, there was an issue with this data acquisition, but fortunately, Kyle, our lab TA, supplied us with accurate data which we used for data analysis. This data was then uploaded to MATLAB, where we generated the CP, CD, and further information for the data analysis.
So, coefficient of pressure versus theta. So here is our theoretical charts of what coefficient of pressure should look like versus theta. You can see on the right, this is if we assume inviscid flow theory is true, we can see that the coefficient of pressure starts at 1 at 0 degrees, and as it works its way around to the backside of the cylinder, it goes down and then comes back up to 1. And you can see this on the left graph too, which also has turbulent laminar theoretical CPs versus theta. So this is our actual data for 150 RPMs, which is about 5 meters per second. And we still have the green graph here, but we've added the blue and red graph. So the red is just the smooth cylinder before we put on the strips. So we're assuming that this is laminar flow. And as you can see, it follows the inviscid flow theory pretty well until about like 60 degrees plus or minus, and then it kind of settles off around negative 1.5. So that means that we're getting separation at that time, and that's what's causing the drag on our cylinder. And then the blue graph is with our trip strips. However, at 5 meters per second, we're really not seeing that much of a difference between the trip strips and no trip strips. So we're thinking that the reason for that is because the flow is not going fast enough for there to be enough energy for the trip strips to actually turn the flow turbulent, and it's staying laminar after the trip. This is our graph for 300 RPMs, which is 11 meters per second. And as you can see, there's a pretty big difference between our with trip strips and without trip strips. You can see that the flow stays closer to inviscid theory on the blue a lot longer than it does on the red. And what this means is that we're getting separation at later angles. At later angles than we are when we don't have the trip strips. And so what that ends up meaning is that we're going to have less drag because we're affecting the flow around the cylinder less with the trip strips. Okay, here is 155 RPM, which is 21 meters per second. We kind of see the same thing as we did with 300 RPM. One thing to notice is that port 4 has been seeming to be acting up, I guess. It's a little bit off. We'll talk about that later, though. And then here's 700 RPM, which is 26.5 meters per second. It looks quite similar to the other graphs, except one thing to notice is that without trip strips, the CP actually it goes down, and then it comes up, and then it goes back down again. And we're not quite sure why this happens. We kind of think that the reason it's happening in the area separation. So our thinking is that maybe there's something that's going on in the separation that's causing the flow to speed back up again, like maybe some backflow or something. But we're not quite sure why it does that. So our general CP trends, the first thing to notice is at low Reynolds numbers and speeds, tripping the airfoil didn't really change the flow because we didn't have enough energy in the first place to create turbulent flow. So it doesn't matter if it's tripped or not. And then at higher speeds, we can see that the CP follows the inviscid flow theory better once you trip it. And the reason for that is because it turns turbulent and it stays attached longer. And then we can see that in the back area of the CP, whether it's tripped or not tripped, the CP is a lot lower, and that's indicating that inviscid flow theory is really not true, and we don't have inviscid flow, and that means that we actually have drag instead of not having drag. Okay.
The Strohal number. The Strohal number is dimensionless, and it can be used to describe the oscillatory tendencies of a flow around a body. While the Strohal number is calculated using frequency, characteristic length, and free stream velocity, it also has a functional relationship with the Reynolds number. Bodies with the same profile, in general, share the same Strohal number when observed at the same Reynolds number. For cylinders, at the range of Reynolds numbers this test was run at, this number hovers around 0.2. Because it is dimensionless, like the Reynolds number, it can help predict the changes in the frequency of vortex shedding by creating a similar flow comparison, allowing one to observe how changes in free stream velocity and characteristic length affect the frequency of vortex shedding. Experimental data revealed a slightly lower Strohal number for the tripped cylinder compared to the non-tripped cylinder. This perhaps suggests a relationship between the drag coefficient of a body and its Strohal number. The difference between a tripped boundary layer versus a non-tripped one becomes apparent with a side-by-side comparison of the flow visualization for each case. In the video of the tripped cylinder, the vortex shedding appears to begin closer to the trailing edge of the cylinder and has less magnitude than when the cylinder is not tripped. This effect occurs because the flow stays attached to the cylinder longer when the boundary layer is tripped, because the tripping energizes the boundary layer, which in turn allows it to stay attached for longer and separate further down the cylinder. Because it separates further down the cylinder, the area that the vortices have to shed from is reduced, resulting in a smaller vortex. The separation further down the cylinder also means that there is more of a vertical component to the flow when it separates. Visually, this can be seen by the formation of vortices closer to the trailing edge of the cylinder.
Drag force and drag coefficient. The drag force on the cylinder increases with increasing Reynolds number for both the smooth and tripped cylinder. As seen in the table, it is significantly less for the tripped cylinder from 300 to 700 RPM, while remaining slightly the same for the 150 RPM cylinder. The drag coefficient, on the other hand, decreases with increasing Reynolds number. The tripped cylinder for 700 RPM also showed a significant decrease in the drag coefficient compared to the smooth cylinder. This is because by tripping the flow, turbulence is generated in the boundary layer to keep it energized and attached to the cylinder longer than it would on the smooth cylinder, as shown in the flow visualization. This creates a less effective area on the back of the cylinder and reduces the drag coefficient. As shown in the graph, the CD decreases with increasing Reynolds number, and there's a significant change between the tripped cylinder CDs and the smooth cylinder. The trend showed that the CD decreased with increasing Reynolds number, and at low Reynolds numbers, tripping the airflow had little effect on the CD, while at higher Reynolds number, tripping the airflow made the CD significantly lower.
Error analysis. Unfortunately, there were several errors in our experiment. Luckily, our lab technician, Kyle, was able to supply us with repeated data where some of these errors were minimized. However, there was still an error in the pressure reading on the 4th and 6th port. We managed to somewhat better this data at port 6 by averaging the 2 pressure readings surrounding it. The systematic error occurring at the 4th port was unable to be mitigated, and we believe this may have been caused due to a blockage in the piping. Unfortunately, this left a spike in the graphs, but after discussing with Dr. Doig, there was little we could do to mitigate this. When calculating the data for the Strohal number, we were unable to clearly count the number of shed vortices, as the refresh rate on the iPhone was just not high enough when coupled with the poor lighting conditions in the wind tunnel. Thus, we were only able to count vortices at one of the slower velocities, hence that is why there is only a calculated Strohal number for the test occurring at 550 RPM. Despite these errors, we were still effectively able to distinguish between flow around a cylinder at different Reynolds numbers, as well as the cause that tripping the boundary layer has on generating wake vortices. Thank you for listening.